These are the answers to homework 5H. Here are the definitions I would like you to know. Now let's go to the questions. Number 1, give the heat of combustion, or given the heat of combustions for the following combustion reactions, calculate the enthalpy change for the reaction 2 carbon plus hydrogen yields C2H2. We're going to perform this by Hess's law, where we're going to take the 3 combustion reactions given above and make them add up to make the overall reaction 2C plus H2 yields C2H2. First, we need 2 moles of carbon on the reactant side. The only equation that has elemental carbon in it is the middle combustion reaction. That has carbon on the reactant side, but it has only 1 mole of carbon on the reactant side. So I'm going to take the middle combustion reaction and multiply by 2. If I do that, I'll get 2 moles of carbon plus 2 moles of diatomic oxygen yields 2 moles of CO2. The delta H for the original combustion reaction was negative 394 kilojoules. That's for the combustion of 1 mole of carbon. And because we've multiplied the reaction by 2 and we're now combusting 2 moles of carbon, twice the amount of heat will be released. So the delta H value will be double the negative 394. It'll be negative 788. Now, next, to get 1 mole of diatomic hydrogen on the reactant side, I'll need to find a combustion reaction from above that has diatomic hydrogen in it. That would be the 3rd combustion reaction. It has diatomic hydrogen on the reactant side, and there's 1 mole of diatomic hydrogen on the reactant side. So I'm going to take that reaction exactly how it's written, and its delta H value will be identical to what it was given above, negative 242. And so now I've fixed both reactants in the reaction I desire. I have 2 moles of carbon on the reactant side and 1 mole of diatomic hydrogen. Finally, I need to get a reaction so I can place 1 mole of C2H2 on the product side. The only combustion reaction that has C2H2 in it is the first one, but the C2H2 is on the reactant side instead of the product side. I'm going to have to reverse the original reaction. So if I reverse it, it's going to be 2CO2 plus H2O yields C2H2 plus 2.5 O2s. Now the C2H2 is on the appropriate side, the product side. Because I've reversed the reaction, that means now the reaction is no longer exothermic as it states above, negative 1257 kilojoules. But when you reverse a reaction, its sign changes as it goes from exothermic to endothermic. So the delta H for the reaction, the way it's written now, is positive 1257 kilojoules. Now that I have the 2 moles of carbon and the diatomic hydrogen on the reactant side and the 1 mole of C2H2 on the product side, I'm going to add the reactions together. In this case, we have some canceling out to do first. First, the 2.5 moles of O2 on the reactant side will exactly cancel out with the 2.5 moles of O2 on the product side. Then, the 2 moles of CO2 on the reactant side will exactly cancel out with the 2 moles of CO2 on the product side. And finally, the 1 mole of H2O on the reactant side will exactly cancel out with the 1 mole of H2O on the product side. This leaves 2C plus H2 yields C2H2. So because I was able to add 3 specific reactions together to make my reaction 2C plus H2 yields C2H2, all I have to do is add the enthalpy changes for those 3 reactions, and that's going to equal the enthalpy change of the reaction that I've desired, because enthalpy change is a state function, which means the process by which the reaction occurs is irrelevant. The enthalpy change will always be the same. So if I pick the reaction to occur by these 3 specific steps, I just have to add the 3 delta H values for those steps to calculate the delta H, or the enthalpy change for this process, which turns out to be positive 227 kilojoules. Question number 2. Using the heat of combustions for C4H4, C4H8, and H2, all numerical values given, calculate the delta H, or the enthalpy change, for the reaction C4H4 plus 2H2 yields C4H8. Problem number 2 is exactly like problem number 1. I've given you 3 heat of combustions, and I want you to take those 3 combustion reactions and make them add up to make this reaction given here in number 2, C4H4 plus 2H2 yields C4H8. The only difference is I didn't write the reactions out for you. I want you to do that. So the first numerical value given to you was the heat of combustion for C4H4. It was negative 2341 kilojoules per mole of C4H4, or negative 2341 kilojoules per mole of C4H4. So that's the enthalpy change for the combustion reaction of C4H4, which means C4H4 plus O2 yields, and you get an oxide of carbon and an oxide of hydrogen, so CO2 plus H2O. Write the balanced equation. That turns out to be C4H4 plus 5O2 yields 4CO2 plus 2H2O. Now, one thing to check is that the delta H value they gave you, the heat of combustion they gave you, was negative 2341 kilojoules per mole. And when they give you a heat of combustion as a per mole value, that means per mole of the substance that burns, which means the C4H4. So as a check here, you want to make sure that your balanced equation is combusting 1 mole of C4H4, because if it is, then the delta H for that process is the negative 2341. If it isn't, you would have to change the balanced equation, so the balanced equation is only combusting 1 mole of the substance. The next heat of combustion they gave you was for C4H8. It was negative 2755 kilojoules per mole of C4H8. So you just have to write the corresponding reaction. If this is the heat of combustion of C4H8, it's the enthalpy change for C4H8 plus O2, yielding CO2 plus H2O. Write the balanced equation, which is this: C4H8 plus 6O2 yields 4CO2 plus 4H2O, and then verify that because the delta H given, the heat of combustion given, was negative 2755 kilojoules per mole of C4H8, that your balanced equation has 1 mole of C4H8, which it does. The final heat of combustion given was the heat of combustion of hydrogen, negative 242 kilojoules per mole. So this is the reaction of hydrogen combusting. It's H2 plus O2 yields H2O. If you balance the equation, you'll have 2H2 plus O2 yields 2H2O, and here's a problem. The delta H value is negative 242 kilojoules per 1 mole of H2. So you have to divide the reaction's coefficients by 2, and the balanced equation H2 plus 1/2 mole of O2 yields H2O is the reaction that combusts 1 mole of hydrogen, and so now the delta H of negative 242 matches with this reaction. If you didn't divide the reaction by 2, if you left it 2H2 plus O2 yields 2H2O, that's the combustion of 2 moles of hydrogen. If you want to write the delta H next to that balanced equation, you would have to multiply the negative 242 by 2, and you could write negative 484 kilojoules, then you would be fine. Either of those would be okay. So now we're just like problem number 1. Here's the 3 given reactions that we know enthalpy changes for. Can we make those 3 reactions add up to my overall reaction at the very top? First, I need 1 mole of C4H4 on the reactant side. So I'll take my first combustion reaction. It has 1 mole of C4H4 on the reactant side. It's written perfectly. I'll write it down exactly how it is, and because I didn't change it at all, the enthalpy change for that process is still negative 2341 kilojoules. Second, I need 2 moles of H2 on the reactant side. The only combustion reaction that has H2 in it is the third one. It's on the reactant side, but there's only 1 mole of it. So I'll have to take the combustion of hydrogen reaction and multiply it by 2, so that it's 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of H2O. And because I've doubled the amount of hydrogen that's combusted, I double the delta H value of negative 242 to negative 484. Finally, I need 1 mole of C4H8 on the product side. The only reaction that has C4H8 in it is the middle combustion reaction, but it's unfortunately on the reactant side, so I will reverse that reaction to put the C4H8 on the product side. When I reverse it, the reaction becomes 4CO2 plus 4H2O yields C4H8 plus 6O2. Because I've reversed the reaction, I'm going to change the sign of the enthalpy change, because if the reaction, the way it's written above, is exothermic, if the reaction's reversed, that process will be endothermic, and an endothermic reaction has an opposite sign as an exothermic reaction, which is positive. So the delta H for this process is positive 2755 kilojoules. If I now try to add the reactions together, first I'm going to try to eliminate anything that's the same on the reactant and product side. So first, I'll notice I have 6 moles of O2 on the reactant side and 6 moles of O2 on the product side. I'll cancel those out. Second, I have 4 moles of CO2 on the reactant side, 4 moles of CO2 on the product side. I'll cancel those out. And then I also have 4 moles of H2O on the reactant side, 4 moles of H2O on the product side. Cancel those out. That leaves the reaction C4H4 plus 2H2 yields C4H8. And by Hess's law, it doesn't matter what the pathway is in order to go have reactants turn into products, because I can make this reaction occur by this 3-step process. All I have to do is add the delta H's for those 3 reactions, and that's going to give me the delta H for my overall reaction, which turns out to be negative 70 kilojoules.